When a gear tooth snaps under load, the physical destruction is immediate and obvious. But long before the metal fractures, the true origin of that failure usually lies buried in the engineering data systems tasked with predicting it in the first place. To map complex risks across a product's lifecycle, standard design for reliability still relies overwhelmingly on static spreadsheets today. This creates an immediate structural deficit. Vital engineering intelligence, like a critical stress tolerance, gets trapped in disconnected silos, hidden from the teams who need it most. Because these documents can't talk to each other, engineers are forced into redundant data entry. A design change in one file doesn't automatically propagate, leading to competing revisions across different departments. This graphic illustrates the legacy problem, a series of isolated vertical columns hitting a hard baseline. When silos and redundant entries hit this wall, critical risks and their corresponding lab tests become completely orphaned from the main design. A flat grid of text simply lacks the mathematical capacity to track the thousands of intersecting variables required in a modern product lifecycle. Solving this requires abandoning linear documents entirely in favor of a relational ecosystem. Instead of flat tables, data is mapped onto a living graph. Every requirement, component function, and validation test acts as a discrete node within a fully interconnected 3D network. Information across this architecture flows bidirectionally. If an engineer adjusts a root parameter, like increasing the operating temperature, that single input instantly recalculates and updates all connected failure modes and testing protocols downstream. By establishing one continuously updating source of truth, the wall between departments is removed. The silo problem ceases to exist. To understand how this architecture operates in practice, we have to trace the construction of the digital thread sequentially, moving from an abstract concept to a physical part. The sequence begins at the absolute origin of any product lifecycle, capturing the voice of the customer. This interface displays the intake process. A top-level requirement, marked here as CR001, is ingested, assigned a priority, and actively tracked within the database. That plain text customer need is then formally translated into structural engineering specifications. These specifications route into the product breakdown structure. In the BOM function mapping, specific hardware, like component 6, the DC motor, links directly to its physical function. Establishing this relationship means the component and its action are mapped exactly once. With this bedrock in place, every subsequent engineering decision, failure analysis, and lab test is structurally anchored to a specific, original customer demand. Once the static product structure is mapped, the system shifts focus toward dynamic failure prediction. Rather than listing isolated failure modes in a vacuum, the architecture builds a continuous failure network. This diagram illustrates the flow of causality. A specific failure cause, like a strain relief iteration, leads directly to a local failure mode, such as a broken wire, which then dictates the ultimate effect on the end user. Historically, manually extrapolating these networks and typing them out into endless spreadsheet rows creates a massive labor bottleneck. The platform bypasses this using an autonomous synthesis engine. Here, the AI Spark processor analyzes raw parameter data to generate proposed risk items. It reads the system context, input signals, outputs, control, and noise factors. From this logic, it autonomously drafts standardized, high-priority risk rows. These drafts are deposited into the master FMEA editor. Here, we can see the action priority column dynamically auto-calculating as it integrates severity, occurrence, and detection linkages. Because data flows through relational pathways, every generated row guarantees AIAG-VDA framework compliance without manual formatting. By automating the repetitive generation of standard risks, the reliability engineer is elevated from a data entry clerk to a strategic risk reviewer. But even a meticulously generated FMEA is vulnerable to the final major flaw of standard design protocols: isolated knowledge and institutional amnesia. Highly effective testing protocols and precise prevention controls frequently end up locked inside individual project files, forgotten the moment the product ships. The central controls library solves isolated data by pushing updates across active branches. Controls live universally in this centralized hub. If an engineer revises an effectiveness rating here, that modification dynamically cascades across every active FMEA globally. This systemic reusability physically prevents disparate product teams from making the same engineering errors twice. Institutional engineering wisdom is captured precisely once and then leveraged endlessly across the entire enterprise. With the components, functions, risks, and controls firmly established, we can pull back to observe the fully constructed architecture. This is the synthesis node. This interactive graph visualizes the massive, multi-directional web of data we've just built. You can trace a single, unbroken line starting from a base requirement, like electrical distribution, moving through a specific vibration failure into a prevention control, and concluding at an exact laboratory test. Looking at this density of connections, the visual proof is clear. Not a single critical risk has been left orphaned. If a supplier swaps a material mid-life cycle, leadership can query this graph to perform an instant impact analysis across all interconnected subsystems. This graph serves as the mathematical proof of absolute structural continuity in risk management. This theoretical continuity must eventually translate into the physical reality of the testing lab. Digital risk analysis directly drives the design verification plan and report. This interface shows how an overarching requirement directly links to the precise operational parameters of a shaft seal leak test. The specific detection controls established within the FMEA mandate the physical environmental constraints of that test. Execution occurs through the Integrated Lab Management System. This rig scheduler Gantt chart explicitly aligns the utilization of physical equipment, like thermal chambers, directly against the highest FMEA risk priorities. By orchestrating environmental chambers and vibration tables according to actual risk profiles, teams actively prevent testing bottlenecks before they form. But operational reality demands compromise. Supply chains, legacy stakeholders, and regulatory auditors will continue to demand static PDFs and standard spreadsheets. To bridge this gap, the system utilizes automated documentation. This visualization shows the complex relational network funneling seamlessly into compliant, linear, CSV, PDF, and Excel documents with a single click. By breathing internally as an advanced relational database, yet exporting as legacy documents, the architecture enforces rigorous reliability logic